Hello, and welcome to the HYDAC Australia podcast. I'm glad you're here. In each episode, we share practical insights, technical knowledge, and real-world solutions to help you get the most from your hydraulic and fluid power systems. Let's get started. Have you ever wondered why two identical hydraulic machines operating in the same environment can have completely different reliability and availability? One runs for years with minimal downtime, while the other seems to be in constant need of repairs. In today's episode, we're looking at one of the most overlooked aspects of hydraulic reliability: contamination. More specifically, where the contamination actually comes from, and why understanding its sources is the first important step towards building more reliable hydraulic and lubrication systems. Let's get started. When people think about hydraulic systems, they often focus on the mechanical components. The bearings, pumps, motors, cylinders, and valves usually get all the attention. Yet every one of these components relies on something just as important: the hydraulic or lubricating fluid. The condition of that fluid is fundamental to the reliable, predictable, and safe operation of industrial equipment. There's a simple relationship that's worth remembering. Technical cleanliness leads directly to improved machine reliability. Improved machine reliability leads directly to improved machine availability. Improved machine availability increases throughput, which increases profitability. It's really that straightforward. Clean oil helps keep machines running, and machines that keep running are machines that continue producing value. So where does contamination actually come from? Many people imagine contamination entering a machine after it's been operating for years in a dusty environment. In reality, contamination of the system can begin long before the machine ever starts. Let's start at the beginning. Manufacturing and assembly. Building a hydraulic system involves a range of industrial processes: machining, cutting, grinding, welding, painting, and sometimes even sandblasting. Every one of these processes creates contamination. Think about cutting steel tube. It creates metal swarf. Grinding produces abrasive particles. Welding creates scale. Painting can leave residues. Every one of these contaminants has the potential to end up inside the hydraulic system if proper care isn't taken during assembly. Hydraulic hoses deserve special attention too. At first glance, they might just look like thick rubber hoses. But inside many hydraulic hoses is a significant amount of steel reinforcement. When these hoses are cut, steel particles can be released internally. If abrasive cutting discs are used, particles from the grinding wheel can also find their way inside the hose. Unless these contaminants are completely removed before installation, they're entering the hydraulic system from day one. So before a machine has even produced its first liter of flow, contamination may already be present. Now let's move to another stage that often surprises people: filling the system with new oil. Here's something many people don't expect. Just because oil is new doesn't automatically mean that it's clean enough for use in a hydraulic system. In fact, brand new industrial lubricants are often dirtier than the cleanliness levels required by hydraulic and lubrication systems. It's easy to assume that fresh oil can simply be poured straight into the reservoir. But doing that can undo all the effort spent cleaning and assembling the system. That's why filtering new oil before it enters the machine is so important. There's also a useful rule of thumb. It costs around 10 times more to remove contamination from a system than it does to prevent it from entering in the first place. That's a simple idea, but it's one that can save both time and money. Another source of contamination is storage. Imagine you've carefully assembled a clean hydraulic system. Everything is ready to go, but instead of being commissioned immediately, the machine is placed into storage. If the system isn't stored correctly, contamination can still find its way inside before the machine even enters service. Storage conditions matter. Protecting a system while it's waiting to be used is just as important as cleaning it during assembly. Once a machine begins operating, contamination doesn't stop. In fact, the machine starts producing contamination of its own. Normal wear creates particles as components interact with each other. Those wear particles then create more wear. It's a cycle where contamination generates additional contamination. The lubricant itself also changes over time. Oxidation byproducts develop during operation, creating further contamination that needs to be managed. This is why filtration isn't something that happens only once during commissioning. It's an ongoing process for the entire life of the machine. Then there's the environment. Even if everything inside the system is operating perfectly, the outside world is constantly trying to get in. Contamination can enter through seals, wipers, and breathers. Even changing a filter element creates an opportunity for contamination if the procedure isn't carried out carefully. One interesting point is air. Because we can see through it, we naturally think it's clean. But compared to the cleanliness requirements inside modern hydraulic systems, normal industrial air is actually extremely dirty. That's why protecting reservoir breathers and sealing systems properly is so important. Now that we've explored where contamination comes from, let's talk about the different forms it can take. The first, and probably most familiar, is solid contamination. Solid contamination includes things like grinding material, rust particles, welding scale, steel particles, iron, bronze, aluminium, fibers from cleaning cloths, rubber debris from hoses and seals, oxidation residue, and particles generated from bearing materials. Not every particle causes the same level of damage. Several factors influence how harmful a particle can be: the material it's made from, its size, the number of particles present, its shape, how the machine operates, the pressures involved, the flow velocity, and finally, how sensitive the machine's components are to contamination. Different machines have different cleanliness requirements. Higher pressure systems, for example, generally require cleaner oil because the internal clearances are tighter and the oil film is under greater stress. Another interesting point is particle size. The human eye can typically only see particles around 50 microns and larger under ideal conditions. Yet many hydraulic filters are designed to capture particles much smaller than that. So a sample of oil might look perfectly clean to us, while still containing contamination capable of damaging sensitive components. Looks can definitely be deceiving. The second type of contamination is liquid contamination. The most significant example here is water. Water is a poor lubricant. It reduces the lubricating film between components and can damage bearings through hydrogen embrittlement. The goal is simple: keep as much water as possible out of the hydraulic system. Water can enter through leaking fluid-to-fluid heat exchangers. It can also enter during lubricant storage. For example, storing oil drums upright outdoors allows rainwater to collect on top of the drum. As temperatures change throughout the day, the drum breathes, drawing moisture inside. A simple practice, such as storing drums on their side with the bungs positioned horizontally, can help reduce this risk. Other fluids can also become contaminants. Mixing the wrong lubricants, whether intentionally or accidentally, can create problems depending on the fluids involved. Finally, we have gaseous contamination. Hydraulic fluids naturally contain some dissolved air. The air itself isn't necessarily the biggest concern, but the oxygen it contains contributes to oxidation of the lubricant. Air can enter a system through loose suction connections on pumps. Because these areas operate under low pressure, they may draw air into the system without creating a visible oil leak. Aerated oil affects system performance. Unlike hydraulic oil, air is compressible. That means the system can become spongy, reducing controllability and potentially affecting both reliability and safety. Another possible gaseous contaminant is nitrogen. If a hydrop pneumatic accumulator experiences a bladder failure, nitrogen can enter the hydraulic oil before eventually leaving the system through the breather. So, what should we take away from today's episode? Hydraulic contamination doesn't have just one source. It can be introduced during manufacturing, during assembly, while filling with new oil, during storage, throughout normal machine operation, or simply from the surrounding environment. Understanding these sources helps us focus on prevention rather than repair. Because in hydraulic systems, keeping contamination out is almost always easier than removing it later. In our next episode, we'll continue building on these fundamentals as we explore another key topic in hydraulic filtration. Thanks for listening to the HYDAC Australia podcast. If you enjoyed this episode, be sure to follow the podcast and share it with your colleagues. For more technical resources and product information, visit hydac.com.au. Thanks for listening and see you in the next episode.